Okay, so here's the first lesson in Unit 6, which is on integration. And so today what we're going to do is we're going to explore approximating areas. Now today it's not going to feel like it's connected to anything that we've done, but it actually will be. So we're going to kind of like take a little sidestep and kind of look at the areas under curves. Okay. Now, one of the things that calculus students encounter is they basically start with what are called Riemann sums. And Riemann sums is eventually going to kind of give you the idea of how integration works. You know, how do you find the area underneath the curve? Okay, so let's start with Riemann sums. I'm going to go ahead and read everything that is on these sheets, and you guys can view it when you feel like it. Let's take a look at the relationship between the graph of a rate of change function and the area of the region between that derivative graph and the x-axis. So yeah, I guess in a way we graph the derivative, so we're going to be using something we've previously done. Consider the tropical cyclone Imelda that brought more than 40 inches of rainfall over a 72-hour period in southeast Texas during September 2019. Example 1. In order to avoid flood water entering your home, you rent a pump that can remove water at a rate of 500 gallons per hour for the first 8 hours of pumping. As the storm grew stronger, you got a second pump, and for the next 16 hours, you could remove 900 gallons per hour using 2 different pumps. Okay, so we're going to actually draw a graph of that. And you can see that we have over time, and then we have actually the gallons per hour being pumped. So the gallons per hour is not how much water is being pumped. All we have is a speed, okay? We have a rate at which the water is flowing outward, okay? And so we've been calling that V of t, okay? So we are graphing the derivative here, all right, which you guys already have experience of. So if we go for the first 8 hours of pumping, okay, that is from here to here, all right, we have a total of 500 gallons. That's the rate. So at 500, I went from, there's 1 hour, 2 hour, 3, 4, 5, 6, 7, 8. Okay? It's just a constant, we turn on the machine and it pumped this amount, this velocity for the first 8 hours. Okay? That's when it had one pump. Now the second pump is now put into play, and the second pump goes for the next 16 hours. So that takes us all the way to 24 hours, right? 16 plus 8. So we actually, as soon as we turn on that other pump, it jumps to 900. And it's going to go all the way to 24. Okay, so what does this mean? This is the gallons per hour pumped. Okay, so gallons per hour pumped, and this is the time in hours. Okay, now I'm going to apologize if you actually accidentally see my arms. I've got like poison oak, okay, like it's bad, and so if you all of a sudden see like this terrible blister and it grosses you out, it's just poison oak, and it's kind of gross, but this is like calamine lotion here, so that's kind of gross. But no, you're gonna have to deal with it, okay? Because it's so itchy. All right. So when we say the area under the curve, which is what I said in my earlier comments, this represents the area between the graph and the horizontal axis. So this is not a curve actually. These are just two rectangles, right? We want to find the area under the curve from 0 to 8 hours, and what does this value represent in context? Okay, to the storm. So what is the area of this curve? Well, if I have 500 and I went for 8 hours, okay, from time 0 to 8 hours, okay, if I multiplied 500 times 8, I get 4,000. 4,000 what? Well, if we were to multiply gallons per hour times hours, okay, you can see how the units actually do cancel out. So what we have is actually gallons. This represents 4,000 gallons got pumped out in that those first 8 hours. I mean, that's a simple math. I mean, it's very simple math, right? What you're doing is you are literally, though, finding the area under the curve, okay? And so this represents how many total gallons were actually pumped those first 8 hours, because you multiplied the velocity times time, okay? So that's just from 0 to 8. Now, if we want the total area, okay, now the total area would also include this. So here we jumped from 900, a rate of 900 gallons per hour, okay? Now we're going to multiply it to the rest of this. Now, this is not a full 24 hours. It's going from 8 to 24. So that actually is 16 hours, okay? And the units, and this should always happen every time, the units should beautifully cancel out, so that you've got 900 times 16. I'm not going to try to do that in my head. All right, and that's 14,400 gallons. Okay, so totally we have 4,000 gallons plus 14,400 gallons is going to give us 18,400 gallons were pumped out total over that 24-hour period. Okay, and that's essentially the gist of what this is all about. Okay, when you have the derivative, you're actually going backwards. Okay, to get, so this would be kind of like, when we had distance, and then we had velocity, and then we had acceleration. All right, if you go backwards from velocity, you find the distance. Okay, and that backwardsness is the area under the curve. Okay. All right, let's move forward. So let's continue with approximation under curves that aren't so linear, okay? So what approach can we take if the rate of change function is not constant, as it was in the previous? We just had flat lines, okay? The two big ideas in calculus are the tangent line problem and the area problem. In the tangent line problem, you saw how the limit process could be applied to find the slope of the tangent line, that is the derivative, at any point on the curve. A second classic problem in calculus is finding the area under the curve that is bounded by the graph, the x-axis, and the two, that should be the x-axis and the two x values. All right. A basic overview of areas as limits. In the limit of rectangles approach, we take the area under a curve, y equals f of x, so any curve, above the interval a to b, by approximating a collection of inscribed or circumscribed rectangles in such a way that the more rectangles used, the better approximation. Finally, the number of rectangles is increased without limit, and bingo, we get the area known as integration. Specifically, we are interested in finding the area A of a region bounded by the x-axis, the graph of a non-negative function, y equals f of x, defined on some interval a to b. Note, the requirement that f be non-negative on AB means that no portion of its graph should go below the x-axis. By using rectangles, we can see that there are three different ways of approximating the area for A. This is commonly known as Riemann's sums. Okay, now I'm going to just kind of give you an idea. There's a picture here. Okay, so you can kind of see here what we're doing. We're using rectangles because it's the easiest thing to calculate. The area of a rectangle is very simple. So notice that here in this first curve, notice I only have 4 rectangles. The approximation is not going to be very good. Okay, and you can see that I picked a particular side for that rectangle for it to be on the curve. But if I added all these areas up, then I'm going to get an approximation, but it's not going to be very good. Now, as I move over here, I increase the number of rectangles, and it's going to be a little better. Okay, as I go to here, a little better. When I get to yellow, it's going to be very good. All right, now this graph in the middle here kind of represents that if I keep moving the number of rectangles and add the number, eventually I'm actually going to get the real area. So what I'm doing is I'm kind of squeezing all of these rectangles closer and closer and closer, so that essentially you have the area. Okay, and that's where the limit that we studied in the very beginning of the year, that's where that's going to come into play. Okay, so let's start. Okay, So consider a 30-gallon aquarium is being filled with water at a rate modeled by this little trig function here. So we got 6 r of t equals 6 sine of pi over 8 times t, where t is in time in minutes and r of t is in gallons per minute. Find the volume of water in the tank after 5 minutes by using 5 rectangles that are 1 minute wide and r of t in height. Okay, so I have the 5 rectangles here. Okay, so let's see here. Let's make a table at time. Here's r of t. And then this is actually going to be the volume at a given time. Okay? Well, actually, I wouldn't say that volume. It's really, no, let's say the area of the rectangle. But in this context, it actually is volume. Okay? So this is the area of the rectangle. Okay? So at, let's see, if I go to time 1. Okay, at time 1, what is, I'm going to use my calculator here, what is r of t? Well, I have to plug it into the function, and since I've got several of them, I'm going to go ahead and, I know you guys don't have your graphing calculators, use Desmos, okay? Or there's, if you got it on your phone, whatever, it should be no big deal. Be resourceful. Now I've got pi divided by 8 times x, and that's it. Close the parentheses, and that's my guy. So table set, I'm going to start at time 0, not 850. I'm going to go up by 1 because it looks like, yeah. All right, and so once I go to, I'll go to ask for quick numbers here. Now I'm going to go to the table. At time 1, looks like I have a height of 2.296. So what's the total area? Okay, now the total area here is 1 times 2.296, which is 2.296. Okay, so now I go to the second triangle. So this one here, okay, going to 2, how high is it? Okay, how high is that? So this is the height of the rectangle. This is the width. Now the width is 1. And the height is actually going to be, well, we got to plug in 2. Okay, looks like it's, when I plug in 2, it's 4.2426. Okay, so what's the width on that? Well, basically, I'm going to take these two numbers and I'm going to add them. And then what I'm doing is I'm adding all of these as I go. Okay, and so I'm going to take those two numbers. Okay, let's go, it doesn't have a clean-cut copy, so unfortunately I'm just going to have to go 2.296 plus 4.2486. Alright, we're going to have 6.5446. Alright, now this is just going to keep going, right? So this is what a Riemann sum does. So let's go back to the table. Okay, I want to hit in 3. At 3, the height has increased to here. Okay, and again, I'm just keeping track. So 3, that height is now 5.5433. 5.5433, so plus 5.433. I get 11.9776, and you can see where this is going. Okay, we're just going to keep adding them as we go. In fact, I do have the numbers here. 5.43.39. It looks like they did some rounding here. So we'll be close to like what this has. Okay. Yeah, it looks like they did some rounding in the beginning so that they actually ended up with 6.539, and then this ended up actually being 5.543. So then when I plugged in a 4, I actually get a 6.0. And this ended up adding it up being to 12.082. I keep adding it as I go. Finally plug in 5 and I get 5.543. Now notice that as we got to 5, this started to go back down again. Okay, so the volume of the water got up to, it started to, let's see, you're filling it, okay, it's increasing. Find the volume of the water tank after 5 minutes, and so the volume started to decrease again. Okay. Now, of course, I just add this up, so 23.625. Now that represents the actual volume, gallons of water that are actually in the tank cumulatively after 5. That's how much is in the tank after 5 minutes. Okay. Using 5 rectangles. Now, here's what's great. This is what Newton did. By using more and more rectangles with smaller widths, that is, taking the width of the rectangle and making them so small, you're essentially making your delta H go to 0. And we've been doing that. So we're going to do it with the width of the rectangles. And so, in fact, if we consider taking this to a limit of accumulating in an infinite number of rectangles, that is, as n goes to infinity, we would arrive at the exact volume of water in the aquarium after 5 minutes. And this is called the definite integral. Okay, definite, because there's definitely a number. Okay, it's very specific and is represented by this notation. Okay, so here we have the symbol here, the very famous. Okay, so we're saying the integral from 0 to 5 of r of t dt. All right, the integral from 0 to 5 of r of t dt. That's how we say it. Okay, that's exactly what we did right here. We went from 0 all the way to 5, represented here to here. Our function was labeled r of t. Okay, now I could have replaced this r of t with that guy right there, but notice that this dt, okay, that time differential, that represents little delta t. Okay, that's what that dt stands for. All right, so there are 3 types of Riemann sums. I can actually go under the curve, I could go over the curve, or I could kind of go in between. All right, now this all depends on which direction your function is going, okay? But we call this a left endpoint or a left sum for an inscribed rectangle, okay? I never use the word inscribed. I'm just going to use a left Riemann sum, okay? Now, the left, you can see that we actually used the point at the left of the rectangle. So we go to the curve, but we put the left of the rectangle at the first position. Okay? Here's the left of the rectangle. I should say the left of the rectangle at the very top of the rectangle. So there's the left part of the rectangle. There's the left. There's the left. Okay? Over here, notice that we have the right endpoint, or the right Riemann sum. And so the right, we use the right side. Okay? Here's this rectangle, we use the right top of the rectangle. Here we use the right top, the right top. Now notice the difference between the two. This ends up being an underestimate. This will be an overestimate. Okay? This guy will be a better estimate. Now, when you think of midpoint here, you might be thinking, oh, well, why don't I just add the left and the right together, take the average, and I'll get the midpoint. No, it doesn't work that way. Which you'll get something else instead, but we'll talk about that later when you add these two and take the average, okay, which is a good idea. You got the upper, you got the lower, take the average. That one is not the midpoint, okay? So we're gonna go over that one later. That's a whole another thing. Okay, so these do require a little practice though, to kind of draw the graph appropriately and then know what you're going to be adding up, okay? Now here is a very fancy equation here. This is the actual definition of the integral. So let's say that f is continuous, no holes, no breaks, okay, on a to b, and f of x is greater than 0. It's positive, okay. Let a and b be partitioned into n subintervals of equal length. So what that means is I'm breaking them into as many rectangles as I want. My n could be 10 rectangles. It could be 100. It could be 1,000. It doesn't matter. Now remember, if n is larger, it's going to take you a lot more time to calculate. A lot more. In fact, you're going to need a calculator to do it if you want 100. But if you have a handful, like 5 is usually kind of 5 to 7 is usually the max that you can do by hand, or after that, when you get to 10, you pretty much use a graphing calculator. And there are programs on these calculators for you to actually do Riemann sums. Okay, and I don't know how you're going to get your hands on those, but I'm sure they have some kind of app online that will do. In fact, they do. They do. In fact, I think they actually draw the picture for you. So I will find that link and find that really cool website, because I remember being kind of pretty stoked when I saw it last year. All right, anyways, so the delta x represents that dt, you know, that little interval that we're making as small as possible. Now here, we're going from, say, in our previous example, we went from 0 to 5. Okay, so this would be a 5 minus 0, and then I'm going to divide by the number of rectangles that I want, and that will determine the width of my actual rectangle. Over here, it was conveniently 1 second each time. No, I'm sorry, 1 minute. Okay, so the width was 1 minute, so I multiplied by 1 every single time. It was easy, right? But that is not always the case. Okay, sometimes your rectangles might only be half of a second or 0.25 of a second, and that's going to be your width, and you have to put that into your formulas. Okay, so then the definite integral of f over a to b is given by this guy right here. Now I'm going to break this guy. Now it looks like it's kind of swearing at me, doesn't it? Looks like you got the F word there. Okay, now what we're doing is we're saying that we have infinitely many rectangles, and we are going from the first rectangle all the way to infinitely many. Okay, so we've got so many that it actually becomes, that represents the width of the rectangle, and this guy represents the height of the rectangle. So this right here is just pretty much f of x. This guy is just the width of the rectangle, and you multiply them. Okay, so we could put a little dot there to make a little bit more sense. You multiply the width times the height, and then you add them all up. Okay, add every single one as you go, and this is really what you got. So this is a little bulky to use every time, so we use this. This is that. This represents adding up all of those rectangles under the graph. That is the area under the curve using infinitely many rectangles. Okay, so it's kind of beautiful, really. All right, and this is why we study limits, because the idea is that we have so many that we've essentially got there. Okay, we have the exact area. Okay, so to do these Riemann sums, you want to draw a rough graph of the function over the interval, okay, which this is our first example here. We're going to use this formula to determine each subinterval length, okay? So again, this is width. Okay, that delta x is your width. Now normally we want this to be 0, right? We want that guy to be 0 so that we get this, okay? Or as close to 0 as possible. Now compute x coordinates of rectangles at either left end or right end. Okay, so we need to kind of make a table. All right, then we're going to compute the areas of each rectangle, inscribed or circumscribed. It depends on if you are above or below the curve. And then what you do is you add them all together. Okay, so find the summation. We add up all those approximate areas. Okay, all right. Okay, where are we at? We're at 23 minutes. Okay, I'm going to do example 3. I'm going to actually stop. I'm going to put this out there. I think that's probably pretty good for today. I'm going to do the rest of this this evening. Okay, so I'm going to put this out there. It'll sit there. You probably can only do a few homework problems, but I don't even want to go through it. Okay, because you guys have like a few days to do this. So let me just do this example. I got to feed my kids. I got to put more calamine lotion on, and then we'll tackle this a little later. All right. Okay, so let's put all this together. Okay. All right. So, looks like we're going to find the area under the graph from f of x equals 1/2 x plus 1. There's the curve, line, on the interval 0 to 5 using geometry. Okay, so we might actually do example 4. This is kind of quick and easy. Okay, so we are going from 0 to 5. Okay. We want the area under that, and that's easy. What geometric shape is that? Don't say a triangle. All right, good. Thanks. It's a trapezoid. Do you remember the formula for a trapezoid? Really? You don't? You should. but everybody forgets this. So the area of a trapezoid, we can do this in one foul swoop. I don't even need this, okay? If I'm going from 0 to 5 and I see a basic shape, okay, I want the formula, okay? The formula is you actually take the average of B1 plus B2, okay? Now B1 in this case is this first guy. This is B2, okay? And what I do is I take the average, okay? And what that does is it basically, when I take the average, I put these guys right in the middle, okay? Then I end up multiplying by the height, and then I have the actual area of the trapezoid. So in this case, let's just fill out the formula. B1, what's that height? It's 1. What's B2? B2 from here to here is actually, looks like it's 3.5. Okay, so 3.5. Now, I am estimating here. Let's just be careful here. What happens when I plug in 5? Is somebody here? Okay, 1/2, that's 2.5 plus 1. So yeah, it is 3.5. All right, so then we divide by 2, and then we multiply by how high it is. No, I'm sorry, not the height, because that's actually what we're taking the base of. What we're doing is we're multiplying by the length, okay? The orientation, like for example, if I were to do this, the height now is this. So I've got this guy flipped on its side. So typically the formula for a trapezoid would have this as an H, okay? But in this orientation, this is your B1, this is your B2. Take the average and then multiply by the height. Now in this case, because he's kind of lying flat, it might be confusing if we call this the height, okay? But it's really the length. So you can leave it H length as long as you understand that you want to multiply by how far, what's the distance between B1 and B2. Okay, in this case it's 5. All right, so we got 4.5 divided by 2 times 5. So that's 22.5 divided by 2, and that ends up being 11.25. And I don't have any units, so the area has to be expressed as square units. Okay, so that's just using the trapezoid formula. All right, okay. Now, it looks like example 4 actually is probably going to take me a little bit longer, and I don't, oh man, this video is too long. Let's actually stop right there. I am coming up. Who's there?